Hello girls, I hope you're staying safe at home. To continue with the metallurgy chapter, today we are going to talk about how metals are refined. Now in the last upload, if you remember, we talked about how the metal was extracted from its ore, the various steps. Okay, so finally when the crude metal is ready, remember that it is not the pure metal. Okay, so the residual impurity that is present with the crude metal must be separated. So that is known as refining of the metal. So what are the residual impurities? You'll find other metals, non-metals like silicon and phosphorus, unreduced oxides and sulfides of the metal will still be present with the crude metal, so they must be separated. So refining is the process by which the crude metal is purified, that is, it is made pure. The different methods of purification, it depends on the nature of the metal, the nature of the impurities present in the metal, and even the purpose for which the metal will be used. First is distillation. Now there are certain metals like mercury and zinc which are volatile. They have a low boiling point, so when they are heated they will go over as vapor. Okay, they will distill over as vapor in the pure form, and the non-volatile impurity remains behind. Zinc spelter on distillation gives pure zinc. So zinc spelter is the crude metal, and when it is heated it will distill over as zinc vapor. Okay, and the zinc vapor is pure zinc. Now next is liquation. Metals like lead and tin, they have a very low melting point. Okay, so they are heated on the sloping hearth of a furnace. You know, furnaces are huge fireplaces. The temperature is very high, so that the crude metal will get melted and it will flow down. The pure metal will flow down, leaving behind the impurity. So this is how liquation is done. You can see the furnace here. Okay, and this is the sloping hearth of the furnace. So when it is heated, the molten metal, the metal will melt, and then it is collected separately, and what remains behind? The impurity remains behind. And of course, if you remember, children, we talked about electrorefining in the electrolysis chapter. So here electrolysis is done. You know, the electrolytic cell is made up of an electrolyte, electrodes, cathode and anode. Okay, and that you find in a non-conducting vessel. And you know, the impure metal is made the anode, and the thin sheet of pure metal is made the cathode, and then the electrolytic is a salt solution of the metal which you are refining, and a little bit of sulfuric acid is also added so that the conductivity or the conductance increases. And you know, the electrodes are put inside the solution of the electrolyte. So when electric current is passed, the metal ions gets reduced into metal at the cathode, and the equivalent or the same mass of anode dissolves from the anode and goes into the solution as metal ions. So the reaction at the anode and reaction at the cathode, which you already know, at the anode you have the impure metal, so the metal will lose electrons to form metal ions, and at the cathode the metal ions will migrate and it will gain the electrons that it had lost, and it will turn into the metal which is pure. So pure metal deposits at the cathode and impurities settle down, forming anode mud. We have already done this in the electrolysis chapter. And you know, there the metals like copper, silver, gold, nickel, aluminium and zinc are refined by this process. So electrorefining, if you remember, children, we did in detail in the electrolysis chapter. So now let us move on to aluminium, how aluminium is extracted from its ore. Okay, so you know, the symbol of aluminium is Al. It is a silvery white metal, and it is the most abundant metal in the earth's crust. It is a very reactive metal, so you will not find it free in nature. It is in a combined state. That is why we need to extract it, because aluminium has numerous uses in our daily life. Now, extraction, how aluminium is extracted. It was Hall and Herold in 1885 who developed the process for extraction of aluminium. Okay, so remember, aluminium is extracted from its main ore, which is bauxite, Al2O3. It is a hydrated aluminum oxide which contains 60% of alumina. Aluminum oxide is alumina, and the rest being sand, ferric oxide, and titanium oxide, the impurities present with it. Okay, so there is a process which is known as Bayer's process, where the ore is concentrated, purified, and the bauxite is, that is Al2O3.2H2O, is converted into alumina, which is Al2O3. So it is the Bayer's process. So when you hear about Bayer's process, remember we are talking about the extraction of aluminium. Now first, bauxite is grinded finely, made into a very fine powder, and then it is heated. You know why? To remove the volatile impurities. And then it is heated under great pressure with concentrated caustic soda, that is sodium hydroxide solution, for 2 to 8 hours at 140 degrees Celsius to 150 degrees Celsius. This process is known as leaching. So if you are asked about leaching, you will write down that bauxite is heated under pressure with concentrated caustic soda for 2 to 8 hours at 140 degrees Celsius to 150 degrees Celsius. So that is leaching. So here you will see that the bauxite dissolves and forms sodium meta-aluminate because of the amphoteric nature of aluminium, and it leaves behind the insoluble impurities, which is known as red mud. Okay, because you know the impurities that is present, ferric oxide, titanium oxide, which gives the red color. Okay, so red mud consists of ferric oxide, sand, and these are removed by filtration because we get it in solution form. And these ferric oxide and sand which remains behind, it is solid, so it is removed by filtration. Now when we dilute sodium meta-aluminate with water, okay, we put more water to it and then we cool it by adding cold water, it gets hydrolyzed to give aluminium hydroxide, AlOH3. So that you get as a precipitate, you get it as a solid, and the other soluble impurities, they remain dissolved in the sodium hydroxide. So sodium meta-aluminate with water, lots of cold water, it brings down the temperature to 50 degrees Celsius. Remember, it was at a high temperature, 150 degrees Celsius, 140 degrees Celsius. Okay, and then we get aluminium hydroxide as a solid. It precipitates out. Now the precipitate is filtered. Whatever remaining impurities are there, it will remain dissolved in the sodium hydroxide solution. Okay, so the precipitate is filtered and then it is washed, it is dried, and then it is ignited. Means it is heated at 100 degrees Celsius to get alumina. So as I already told you, aluminium is aluminium oxide. So aluminium hydroxide, it is heated to 1000 degrees Celsius to get alumina or aluminium oxide and water vapor. Okay, so the filtrate which contains sodium hydroxide is again reused, okay, to extract aluminium from bauxite. So that is reusable. Now aluminium oxide, due to its great affinity for oxygen, is a very stable compound. Okay, so it cannot be easily reduced by common reducing agents like carbon monoxide or hydrogen. So again, electrolytic reduction was chosen as the method for reducing aluminium, but they faced a lot of difficulty to obtain aluminium from alumina by electrolytic reduction. Why? Because you know electrolysis or electrolytic reduction must be done in the melted state, and alumina melted at 2050 degrees Celsius. But what happened at this temperature? Aluminium vaporized. Okay, it turned into aluminium vapors. So it was not very easy to collect aluminium. and later this difficulty was removed by Hall. He found a suitable solvent in another ore of aluminium, which was known as cryolite. Okay, so this is the formula of cryolite. So when he applied the current to the molten mixture of alumina, he took 20% of alumina, cryolite he took about 60%, and calcium fluoride 20%. Then he saw globules of shiny aluminium appearing at the cathode. So it was, the difficulty was overcome in that way. So let's see how electrolytic reduction of fused alumina is done, and the process is known as Hall-Herold's process, Bayer's process. We are changing the bauxite into alumina, and electrolytic reduction is known as Hall-Herold's process. So the electrolytic cell was a rectangular iron tank with sloping bottom. The sloping bottom of the tank, now it helps in the removal of the molten aluminum so that it can easily slide down. That is why it is sloping, and the tank is lined with gas carbon. Now the electrolytic use, I already told you, molten alumina 20%, cryolite 60%, and fluorspar 20%. Okay, and then again powdered coke was also sprinkled over the surface of the electrolyte. Why? I will tell you later on. Now, as you can see, the temperature of the molten electrolyte has come down from 2050 degrees Celsius to 950 degrees Celsius. So there was great success is bringing down such a high temperature where the aluminium turned into aluminium vapor. That temperature was brought down to only 950 degrees Celsius. So the molten electrolyte was kept at 950 degrees Celsius by electrical heating. Okay, the voltage used was 5 to 6 volts. Okay, because a low voltage is used so that the molten cryolite does not decompose. Okay, that is, it does not change, it remains the same. So this was the the apparatus used for the electrolysis of aluminium. So we already discussed that. Gas lining was the cathode, electrolyte here, the malt there, this is sloping here, you can see. Okay, so that the melted aluminium flows down and it is easy to collect. So the reaction that took place in the electrolytic cell, what were used? Cryolite, which broke down and gave sodium and aluminium as positive ions, fluoride as the negative ions, fluorspar, calcium fluoride, calcium positive, again fluoride negative, and aluminium oxide gave aluminium as the positive and oxide as the negative ion. So I already told you positive ions, sodium, calcium, aluminium, negative ions, fluoride and oxide. So you know that aluminium is lower in the electrochemical series, is preferentially discharged at the cathode while oxygen at the anode. So the inner lining, the carbon of the electrolytic cell is the cathode. Remember, which is the cathode in this case? The inner carbon lining of the electrolytic cell. So here what happens? Aluminium goes towards the cathode, C to C, and it gains electrons, the electron that it had lost to form the aluminium metal. And what is the anode used in this case? Thick rods of graphite are suspended into the fused electrolyte, which serves as the anode. So here the oxide ions will lose the electrons that it had gained and turn into oxygen atoms. The two oxygen atoms will come together to form one molecule of oxygen. Okay, now here these 4 molecules, 12 molecules are given accordingly. Now 3 is here, 3 4s are 12 electrons. Okay, so anode is oxidized to carbon monoxide, which further forms carbon dioxide. So what happens to the anode? It becomes oxidized. Okay, it turns into carbon monoxide because anode is made up of carbon linings. So the carbon, it will get combined with oxygen, which is coming out at the anode, and it will form carbon monoxide. So carbon monoxide will further react with oxygen to form carbon dioxide. So that is why the question will come and explain why anode has to be replaced from time to time. So this is your answer. So the anode has to be replaced from time to time as it gets oxidized by the oxygen evolved at the anode. Now when the supply of alumina decreases, the voltage suddenly jumps from 40 to 60 volts because we've taken only 20% alumina, so it will decrease. So what you'll see, a jump in the voltage from 40 to 60 volts. So if a bulb is attached to the apparatus, it will glow very brightly. So then it is an indication that new fresh alumina must be added in the electrolytic cell. So whatever aluminium is obtained here, it is 99.8% pure. And further purification, if needed, is done by electrolysis. Okay, now comes the attached question to extraction of aluminium. Why is cryolite used? Your answer: it lowers the fusion temperature from 2050 degrees Celsius to 950 degrees Celsius, and it also enhances conductivity. Okay, and fluorspar and cryolite, what is the use of this in this extraction of aluminium? It acts as a solvent for the electrolytic mixture. It also increases its conductivity because pure alumina is a non-conductor of electricity. Remember that, children. Does not conduct electricity. So fluorspar and cryolite is used to increase the conductivity. And remember, coke or carbon was sprinkled over the surface of the electrolytic mixture. So why is it sprinkled over the surface of the electrolytic mixture? Because it reduces heat loss by radiation. There should be no heat loss by radiation. Why? Because it will bring down the temperature, and we need the electrolyte to be in the molten state. Okay, and it also prevents the burning of the anode. Okay, so refining of aluminium is not there in your children. Your assignment for today is to write down the Bayer's process. That is how the ore, that is bauxite, is changed into alumina, and then to write down the electrolytic reduction of fused alumina, that is the Hall-Herold's process. And please mention all the equations and also the uses of cryolite, fluorspar and powdered coke in the electrolytic reduction of fused alumina. Okay, so next we move on to alloys. Now you know what an alloy is. To define alloy, it is a homogeneous mixture of two or more metals or of one or more metals with certain non-metallic elements. Okay, so another alloy is known as amalgam. It is an alloy only, but it is a mixture or an alloy of mercury. You know, mercury is the only liquid metal with a number of other metals or alloys such as sodium, zinc, gold and silver, as well as with some non-metals, is known as amalgam. And remember, children, dental amalgam is a mixture of mercury and silver tin alloy. Okay, and mercury is stored in iron bottles. Why? Because mercury does not form an amalgam with iron. That is why it is stored in iron bottles. Now, why are alloys made? There are so many metals there. We can make use of the metals, but still alloys are made. Why? It is done to change the property of the major constituent to achieve a specific objective. First is examples. Strength of iron is increased when it is turned into steel in alloy. Brass becomes stronger than its components, copper and zinc. Aluminium bronze looks like gold. Nichrome, it is an alloy of nickel, iron and chromium, is more resistant to electricity. Carbaloy, which is an alloy of tungsten, carbon and cobalt, is as hard as diamond. Bell metal, made up of copper and tin, is more sonorous than copper or tin. That is, it will make more sound, the noise is more better, the sound that it makes is much more better. Okay, alnico is an alloy which is made up of aluminum, nickel and cobalt, and it has very tensile strength. It can lift 60 times of its own mass. Solder is an alloy of tin and lead. Okay, and tin lowers the melting point of alloy. It melts at 180 degrees Celsius. It is used for making electrical connections, soldering purposes, because its melting point is lower than the individual melting points of both the component metals. Type metal is an alloy made up of lead, tin and antimony, which also has a low melting point and can easily be cast. It is used for printing. And sodium amalgam, that is sodium and mercury, is less reactive than sodium. So it is a liquid alloy at room temperature. One word answer. Keep in mind, name a liquid alloy. Your answer will be sodium amalgam. Okay, and so why are alloys made? It is made to improve the specific usefulness of the primary component. Primary component means the main component that is used in making the alloy, and it is not, the purpose is not to adulterate or degrade it, but instead it is used to improve the usefulness of the components. Now, reasons for alloying, depending on the purpose for which the alloy is used. Okay, it is either used to modify appearance and color. Aluminium bronze, it is bright yellow, looks like gold, it resembles gold. To modify chemical activity, sodium amalgam, I told you, is less reactive than sodium. Next is to modify casting ability. Type metal, lead, tin and antimony expands on solidification and can easily be cast. It can be made into different shapes. To lower the melting point, solder, lead and tin melts at 180 degrees Celsius, which is lower than the melting point of lead or tin. To increase the hardness and tensile strength, brass, duralumin has a strength up to 6 times greater than pure aluminium. And to increase the resistance to electricity, nichrome, okay, has resistance to electricity. It can produce much more heat than copper. Okay, now, there are different methods of making alloys. First is by fusing the metals together. Brass is made by melting zinc and copper, and they will be made into one single mass. By compressing finely divided metal, wood metal is an alloy of lead, tin, bismuth, cadmium powder and it is a fusible alloy. Okay, and this alloy is used in automatic sprinkler, which provides a spray of water to prevent fires from spreading. Okay, so it helps in to prevent fires from spreading. Okay, then alloys as solid solutions. Alloys are said to be a solution but in solid form, where in which the metal with a higher concentration is the solvent, like water. In water, if we are talking about a normal liquid solution, you know water is the solvent. So when we look at a solid solution, we will look at which metal is more. Okay, so the metal which is at a higher concentration is the solvent, and the other metals with less constituent is the solute. Now, brass, when we talk about brass, we know it is a mixture of zinc and copper. Okay, so copper is more, so copper is the solvent, zinc is less, so zinc is taken as the solute. You know, solute is the solid which dissolves in the solvent. So in this case, copper is more, so copper is the solvent, and zinc is less, and zinc is the solute. Okay, so now this table 7.2 is important for you, okay, where you will see the common alloys, their composition, properties and uses. So the ones which are ticked you will have to learn, because and the others which are not ticked is not there in your syllabus. Okay, so the main metal, that is the solute, is aluminium. So here the name of the alloy is duralumin. It is made up of aluminium, copper, magnesium and manganese. The property is it is light but very strong as steel. It is hard and resistant to corrosion. It does not rust easily, and it is highly ductile. You know what ductile means? You can turn it into very thin wires. Okay, and you can all yes, it is, you can, like, very thin wires, it will not break when you're turning it into wires. And uses, it is used in making the bodies of aircraft, buses and tube trains. It is used for making light tools, and it is also used for making pressure cooker. So you have duralumin at home, because I guess all of you have pressure cookers at home. Next is stainless steel. It is made up of iron, chromium, nickel and carbon. It resists corrosion, it does not get rusted, it is lustrous, shiny, and it is hard. All of you have seen steel at home, stainless steel utensils at home. It is resistant to acids and alkali. It will remain shiny all the time. And the uses, it is used to make utensils, cutlery, ornamental pieces and even surgical instruments. Okay, next is brass, which is made up of copper and zinc. Okay, more percentage of copper, as I told you previously, less of zinc. So this is the solvent and this is the solute. Okay, it is malleable and ductile. It can be beaten into very thin sheets and drawn into wires. It can easily be cast. You can turn it into any shape that you want to. So it is used to make decorative hardware and utensils. It is also used to make screws and handles. It is also used to make cartridges, containers, parts of watches and taps, musical instruments, electrical goods and marine engines. Okay, next alloy is bronze, which is made up of copper, tin and zinc. It is hard and easily cast, can take up polish, it can become very shiny. Okay, and resist corrosion. I told you it does not get rusted easily. It is used in making medals, statues, utensils, bearings and coins. Okay, bearings are tiny, very tiny wheels which is used for different purposes. Okay, and next finally you have solder or fuse metal. It is made up of lead and tin, 50-50. Okay, it has a low melting point, high tensile strength, it is very strong, and it is used for welding and fuse purposes. So with this, children, we come to the end of the metallurgy chapter. Okay, please add this table to your assignment as well. So until we meet again, children, stay safe. God bless you.